स्ट्रीम नहीं करनी। कर्सर हटा दो वहां से। डॉक्टर ब्रूनो, एम आई ऑडिबल टू यू? सर नहीं है, फोन नंबर नहीं है मेरे पास। क्या हुआ? नहीं नहीं, चलने दो। पॉज करने का ऑप्शन है, पॉज कर दो। हाँ। क्या है? मीटिंग में होंगे। 5 मिनट वेट करते हैं, स्टार्ट करेंगे फिर। Please stay connected. Dr. Bruno will be joining shortly for the session. यूट्यूब पे चेक करो, पॉज हुआ है कि नहीं। फोन पे चेक करो। मैं जो बोला था। कर दिया। क्या बदतमीजी है, क्या बदतमीजी। पाँच बजे ज्वाइन करेंगे क्या? 5 बजे ज्वाइन करेंगे क्या? कर दिया नहीं कैसी। कॉल कर रहा है क्या? Hello. Yes, sir. Good
Hello.
evening. Yes.
Yes. Hello. I correct.
Yes, sir. Welcome back to the session. So you may present your screen
Yes.
and proceed.
My screen is here. Can you see it? Can you see my screen?
Uh, it's loading, sir. It'll take a minute. So please share your full screen.
Can you see?
Not yet, sir.
Okay. I hear you.
Yes, sir. Sir, still we are not able to find your screen. Can you reshare it? Stop sharing and reshare it. It will fix.
I stop sharing and
Yes.
I reach share. Okay. Let me know if this is fine.
Uh, yes, sir. We are not able to see yet.
It should be good in a few minutes.
Yeah.
What happens?
Sir, you shared your screen and then you opted for full screen, right?
I share my screen. Yeah.
Then you chose full screen sharing, right?
Yeah.
Yeah. Okay. Still, it's not visible to us.
This is full screen.
Uh, so when you shared, you got two options: full screen and Windows. Hello, sir.
Windows.
Yeah.
Is
You
okay.
so you
Can you see it?
yeah you choose full screen, then it will be visible to us. It will take a minute, I guess. There is a network lag. Yeah. Yeah. Yes, sir. Now we can see your screen. It's visible to us.
This
Yes.
is full screen. Can you see it?
Yes. Yes, sir. I can see your screen. You can go to your presentations.
Okay, excellent. So, because I want to make the link between the block copolymers and graft copolymers, I would like to underline this review paper regarding the macromolecular engineering approach for preparation of new architectures
So
from
sorry,
fluorinated olefins.
sorry for the interruption.
Sorry,
Can you just minimize your windows and just so that we can see the presentation?
you want me to minimize
Just the
like this?
browser or team, so that we can see your screen presentation. We can see your screen, but not the presentation slides.
And here, can you see?
Sorry, it's loading. It will take a minute. Sir, have you reshared?
Yes,
Okay.
I don't know if you see it now.
No, sir, we are not able to.
I don't know what's happening. Ah,
Sir, just follow the same steps which you did in the last session. It was moving flawless. That was great.
I go to window.
Yeah. Then yes, sir. Yes, sir. It's visible. Just make it.
Got it?
Yes, sir. Just make it full screen. Yeah. Yes, sir.
This is good.
Yes, sir. Yes, sir. It's good. You can make it in the slideshow and you can proceed. It's perfectly fine now.
Okay, that's fine. So is it okay like that?
Yes, sir. We can continue.
Okay. I'm sorry for that, and again, I thank you for your patience. In order to make the link between the block copolymers and graft copolymers, I would like to underline two papers, two reviews in which you can find a lot of useful information which are related to my presentation. And the first one is this review co-published with the group in IIT Bihar with Professor Banerjee on macromolecular engineering approach for the preparation of new architectures from fluorinated olefins and their applications. So as you can see, we talk about a different methodology. The Xanthide, the ITP, I have not mentioned, sorry, the cobalt-mediated radical polymerization, but it works too. With architecture control regarding homopolymers and copolymers, and of course the applications. And also a quite recent one, which has been co-signed with a group in China with Professor Chen on fluoropolymer nanoparticles synthesized via reversible deactivation radical polymerization and their application. So this is a quite new recent paper. It's online, you have a DOE here, and you can find also very useful information. And of course, all the different techniques of RDRP, and of course PISA, which is a polymer-induced self-assembly, and related to copolymerization or polymerization of fluorinated monomers, whatever they are, olefins or acrylates of steric derivative and nanoparticles. So for many applications, of course, for biomedical application, MRI, for electrical storage and conversion, etc. Now I'm going to speak about graft copolymers. And as I mentioned before, you have different design of macromolecular architectures regarding the stars, regarding the branching, regarding the ladders, the cyclic compounds, networks, of course, if you cross-link or not. I've mentioned block copolymers, you have random copolymers, alternating copolymers, graft copolymers, and today we are going to focus on that in the following hour. Of course, it's important to consider the functionality in order to undergo further reactions. You know, I mentioned that, for instance, by amidification or esterification, it's possible to make some block copolymers. And it's absolutely the same for graft copolymers, because if you have some pending group, it's possible to attach a chain, and you have a downlink group which can be which can lead the grafts. The microstructure, we speak about stereotactic, atactic, heterotactic. I'm not going to speak about that. And because I'm not going to speak about dienes, I will not mention the stereochemistry regarding the trans, cis, E, Z, etc. So this lecture, I'm going to focus on graft copolymers. So how can they be prepared? This scheme shows different proposition. So either you have a macron monomer, which is a monomer with a double bond containing a long chain, which can be copolymerized with M1. M1, for instance, is a fluorinated monomer, just like TFE, VDF, or other, or CTFE. And it has to react. I mean, what is very important is the reactivity ratio, because I've not mentioned a lot, but it was yes, it was on a slide last Friday that you remember I mentioned 5 different reactions of copolymerization of VDF with fluorinated acrylates. And according to the position of the fluorine atoms, you can have a very high efficient reactivity of a fluorine atom of this monomer or a poor. And the thing is, if M1 is the fluorinated olefin you want to copolymerize, for instance, VDF, CTFE, or TFE, he has to be this has to be more reactive than the macromonomer. This is very important. So in this case, you are going to make poly M1 and P2 will be pendant. You have also some macro chain transfer agent, which are able to start the reaction. Just imagine if you have CF2I, for instance, here, or CCl3, then it's possible with CF2I to do some iodine transfer polymerization, or to do some HRP if you have CCl3, or if you are aromatic BR, or anyway. Another thing is the grafting from. This means that you can react, you can have some reactive group, and then you allow the polymerization of M2 from that. And you can have also some transfer to the polymer, in which you have some labile proton, which are able to trap some polymeric of M2. And in this case, you will have poly M2 here. Another thing also is to take a polymer having some different functional group, which can be able, G, which can be able to react with G prime polymer. And in this case, you are going to set up with this polymer graft copolymer. So you see that you have different technology, and also one I would like to focus on this primary slide on the in ionization radiation, because you know, with cobalt-60, with ozone, and I will give you some example, it's possible to generate some radicals or peroxide or hydroperoxide from which the graft copolymerization can start. So
sorry for
one example is
interruption.
here. Yes?
So we can see your screen, but the slides are not changing. Can you just click on the PowerPoint presentation and make it full screen? Because everything we can
This
see.
is full screen. This is full screen for me.
Now it's changing, sir. Can you just yes, yes.
This is good?
It is loading, I guess. So you just click on the PowerPoint app and then you can change the slide. I guess there is a network issue, that's why it's not changing. You can just yeah, you can continue this way, sir. We can see at least the
Are you
slides
okay?
changing. Yes, sir, fine.
Can you see? And if I put full screen, can you see this full screen?
No, sir, actually the full screen is lagging. So you may continue in the mini version. At least it's changing and we can relate to the topic. So can you just change the slide so that I can confirm?
If I change here?
Yeah, it's changing. So you may please continue in this mode. We will connect to the topic. Thank you, sir.
Okay, no problem. So this means that you have not seen this this slide.
Yes, sir. If you guys just
In the previous.
yes.
Okay, you didn't mention that. Okay, just to mention that we these two reviews. This is in Progress in Polymer Science 2020 with Professor Banerjee. We published a paper on the different architecture from fluorinated olefins and their applications, in which we mentioned the different modes of synthesis, the different architectures, and the different applications. Whatever fuel cell membrane, lithium-ion batteries, and nanocapacitors, hydrophobic, amphiphilic, etc. Now, this is a more recent review which is online, you can find it. It was with collaboration with Professor Chen in China. And this is more derivative on fluorinated nanoparticles synthesized by RDRP and their application. And as you can see, a lot of biomedical application, MRI. Can you see my cursor? Can you see my pointer?
Yes, sir.
Okay. There were also applications on lithium-ion batteries, on fuel cell membrane, on different way of coatings, and also surfactants. Now, today I'm going to talk about graft copolymers, and as you know, there are different macromolecular design ranging from homopolymers to copolymers, block copolymers, random, etc. Okay, I don't insist on that. And this is a major slide in order to show the different methodologies in order to prepare the graft copolymers. This can be a macromonomer copolymerized with M1. This can be a macrotelogen in which you can have, for instance, CF2I or CCl3, which are able to allow some HRP or ITP polymerization. You have a macromolecular way of grafting from A. You are going to allow, this is a reactive group which is able to start the polymerization of M2. You have also the transfer to the polymer, in which the macroradical from M2 is going to be quenched, or in which this labile proton, so this polymer chain will lead some radicals enabling the polymerization of M2 in the system. And then you have also this possibility of chemical modification by the different functional group G able to react with G prime containing a polymer. And in this way, you can prepare these graft copolymers. So one technology is related to the activation by irradiation. And in this case, you can see a polymer chain can undergo some ionization, which can be done by cobalt-60 or by ozone or by other fast X-ray bombardment beam. And this generates some macroradicals on the system, or macroperoxide or macrohydroperoxide, which are enabled to initiate with a monomer grafting from chain. Is it okay now? Can you see?
Yes, sir. Yes, sir.
Okay, great. So this strategy has been used on many substrates based on fluoropolymers. I just take an example with PVDF, and this is the group from Suldon in Finland. They use, I'm sorry I didn't put the reference, but in this review we published a couple of years ago with my PhD student, we fluorofunctional polymers for fuel cell membrane. A lot of examples have been included in this review. And for instance, this group in Finland used some PVDF films that they irradiated under gamma ray at, let's say, 100 to 100 kilo gray to make some hydroperoxide or peroxides, from which they heat it up, and they use styrene first in order to make some PVDF graft polystyrene, which was also chlorosulfonated in order to have some sulfonic acids. So this was interesting because this is a polymeric backbone based on PVDF, and the graft were some polystyrene sulfonic acid. The sulfonic acid enables to lead some conductivity. And the conductivity were not as high as that of Nafion, which is the main product I mentioned. I spoke about Nafion last week, but indeed it's a cheaper way to prepare some graft copolymers and to have some original membranes. This similar strategy was also applied with chromethyl styrene and or vinylbenzyl chloride, And this researcher used electron beam on PTFE or PVDF, okay, making some radical, adding some growing polyvinyl benzene chloride, from which they could allow some HRP by the CH2Cl in order to have some polystyrene side chain on each chlorine of the chain. And then after sulfonation, chlorosulfonation, as before, they were able to prepare some this PVDF graft poly styrene sulfonic acid. This is Holmberg, also the same group in Finland. They did the similar strategy on this one. Reaction with ozone also unable to have some this ozonization led to some hydroxy peroxide, and with, for instance, this NVP, it was possible to have some poly NVP graft onto PVDF, okay, and even this offer add some xanthate in order to allow some chain extension with, for instance, this acryate, dimethylamino acryate, in order to have some new material. So this was for membrane for water purification, because what is interesting, you have you have a hydro some both a hydrophilic and also hydrophobic backbone here. And in this case, it's possible to have some selective passing of water in order to make a desalination. The same strategy was used by Chen 20 years ago. Ozonization of PVDF, making the same systems with this kind of oxone and hydroperoxide. They use on that this xanthate in order to have some xanthane modification, from which they could make some polymers of different hydrophilic monomers, just like a PEG metacrylate, in order to have a backbone, fluorinated backbone, and side groups made of PEG metacrylate for water purification. Can you hear me?
Yes, sir.
Okay. So regarding the industry, I would like to mention a very interesting example from Central Glass. Central Glass did a copolymerization of an allyl peroxy compound with a fluorinated monomer, just like it can be CTFE, TFE, or VDF. Of course, that in the patent, they claim a lot of different monomers. So they did this reaction at low temperature in order to be sure that this allyl group, which is very interesting because allyl, allyl monomers are not so reactive as vinyl monomers. And this is also a main question regarding the reliability of this patent. But I mean, they claim that you have a fluorinated backbone and the side group is linked to this peroxide, peroxycarbonate peroxide, from which they could start the insertion or the initiation of a monomer B in order to stop the polymerization and to have polymer B graft copolymers on this fluorinated backbone. So the question is also, they should also generate a lot of homopolymer B from this reaction, because as you know, when you have a peroxide that you polymerize, you initiate the polymerization, so you do a lot of homopolymers. So there are two main questions in this. What about the allylic transfer, also the poor reactivity of this allylic and the presence of unavoided homopolymer. They claim that the soft segment is a polymer based on CTFE and VDF with a low TG, and they have hard segments with PVDF, so they use VDF as monomer B, and they consider as an industrial product called Central Soft. First, they claim a Japanese patent, which was extended the similar as US patent. So they make some semi-transparent elastic sheets, and they show that they had a better strength and irrigation and break than those of commercially available fluoroelastomers. So this is, there are not so many industrial examples of fluorinated graft copolymers. Okay, the next example is also a direct use of a macromonomer. So we did some work 20 years ago on in collaboration with DuPont, which supply us with this kind of allyl-amido compound containing hexafluoropropylene oxide. This is a Krytox derivative from DuPont, now it's Chemours, and we've been able to make some clear polymers with this allyl compound, allyl-amido, VDF, and HFP to make some graft copolymers on which the backbone is a copolymer of VDF and HFP, and the grafts are perfluoropolyethers. And of course, one application I suggested to the DuPont company, I suggested to use this sample in order to make some blends between some Viton, which are copolymers of VDF and HFP, and perfluoropolyethers, because they sell some Krytox derivatives. So if I put full screen, can you see that? Can you see? Can you see full screen?
No, sir. Actually, there is a problem in full screen.
And here, can you see the slide?
Yeah, here we can see the slide. It's changing properly. You may continue, sir.
I have sorry?
You may proceed, sir.
I have mentioned. Okay, thank you. I've mentioned there are several methodologies. So the methodology we saw for ITP in my first presentation today with RTRP, I will come back later, and on raft polymerization also. So we did in the lab with Dr. Maguire, we did some work starting from methacrylate containing PVDF. And this was prepared by a Michael addition of xanthate onto a methacrylate containing a double bond. And this indeed could be used in order to make some contraradical polymerization in the presence of the tritocarbonate and MMA in order to have a chain extension. And then it was possible to make some graft copolymers with PVDF side groups. So the paper has been published 7 years ago, and I didn't show the SEC or for different system, but indeed when you make you can make even a chain extension with MMA to have a die block copolymers. We have been inspired, and a lot of researchers have seen this paper first published by Zhang and Tom Russell at UMass. And this graft polymerization by ITRP from copolymers based on VDF and CTFE. Indeed, we worked a lot on CTFE, especially on telomerization, and we tried to make some chemical modification of a bivacurine, but the CCL bond is very stable. And indeed, when we read this paper, we were very surprised that it was possible to make some graft copolymers by cleaving this CCL bond. But as you are going to see, there are many papers and many reports on this strategy. And now I know Tom Russell, and I asked him, if you send me the NMR, I can be convinced of your reaction. But he showed me a free NMR, of course, in which we can see the CF changing. So usually the CFCl in PCTFE is about -110 ppm. When you change to here, it goes to -180. And indeed, I didn't see the signature of a signal at -180. So I was a little bit doubtful, and the spectrum was rather ugly. Definitely, they didn't use free NMR, which is the clue in order to understand if this reaction occurs. But anyway, as you are going to see, there are many reactions in this way. I will go a little bit further in details. There is a nice work developed by Slade and Varco in UK, in which they made some gamma ray irradiation of PVDF in order to make some macro radicals, and then using vinyl benzene chloride, it was possible to make some graft. So they changed that into other monomers in order to have a chain extension of many other monomers, and could design different products, which were very interesting. Especially Slade and Varco worked a lot on alkaline fuel cell. In this case, alkaline fuel cell is not devoted because the PVDF is sensitive to base. So in this case, they change to over substrate, and the irradiated ETFE compounds, for instance, or TFE ethylene, or CTFE ethylene, or even other products. Okay. We've been doing some chemical modification in collaboration with a group in Marseille. And indeed, the PVDF was changed in the presence of nitroxide. This nitroxide is very efficient. And we showed, I was very surprised, even we saw that by NMR, we showed that it was possible to withdraw some protons, hydrogen, in the backbone of the PVDF to make some PVDF containing this nitroxide. And this is the signature of the product, in which we have the characteristic signal of PVDF here. This is a proton NMR, and the presence of the nitroxide, this specific nitroxide with this aromatic group and this methyl. I was very surprised because usually the methyl are very electrodonated, and I didn't understand how it was possible to make some reaction onto the hydrogen of CH2 of PVDF. Anyway, indeed, by using this product, I mean, the IR is very good because we see the double bond of CC, and we make some double bond here. The styrene polymerization in presence of nitroxide under NMP is efficient, and we have been able to see, whatever by GPC or by NMR or by IR, to see that we were in the presence of PVDF graft polystyrene. Okay, so this is we had this collaboration with colleagues in Marseille because Professor Guimes has done a lot of work on NMP with different nitroxides. The another work, so which is almost similar, I mean, we have been inspired by that, was from Kilua in MIT. They decided also to use some nitroxide in order to react onto PVDF to have this kind of temple reactive, and then from that to add some by esterification to make some dimethylbromine, which was able to start the initiation of MMA or other systems, butyl acrylate or dimethylamino ethyl, etc. So this strategy is very interesting, but again, I was not convinced by the characterizations of this PVDF containing temple. Though there were nice NMR and also GPC showing that it was possible, of course, to make the HRP of MMA or other monomers in the presence of copper, etc. So I show you a lot of strategies in this way. Again, Lee, in this paper published in Science Advance, took also some PVDF and reacted some tertiary butyl acrylate by HRP, showing that it was possible to make some grafting. I was very suspicious on that also. We have to be critical in the papers. Otherwise, many things can be published. And as a reviewer, I found very often things which do not deserve to be published. So these authors, these are Korean authors, they show by NMR. This is very little also. There were no expansion. Usually we need to have a clear spectra. I was not very happy with these results. Of course, you can see what is called the tail-to-tail addition and the head-to-tail addition of PVDF here. But here it's more or less the same, so I was, and even the presence of DMF inside, so the presence of water, how can you see in the spectrum? This is very, very strange, to my opinion. So they also monitor the reaction by IR to see some specific groups. Of course, IR is not quantitative or difficultly quantitative, so and it's difficult to see. Indeed, the presence of CFH here can be seen by fluorine NMR. Unfortunately, this paper didn't provide any fluorine NMR spectrum, which could see the evidence of the CHF in this way. Another paper in the same strategy was from He in China, in order to make some HRP of glycidine methacrylate onto PVDF, always reacting onto the CH2, and to evidence that they have some oligo glycidine methacrylates here, and even they could change the bromine into azido in order to make some specific click chemistry with other RGD, which is arginine, glycine, aspartic acid, containing a triple bond. So they have been able to adhere onto PVDF some RGD in the context here. We developed also by HRP different molecules and different graft copolymers. First, we started from this vinyl dodecafluoro compound containing bromine by radical polymerization at rather low temperature in order not to have any transfer reaction here, in order to prepare this copolymer based on VDF and this bromo-fluoro compound. And from that, we have done, first we did some model reaction on C6F13BR to be sure that it was possible to make some styrene polymerization. And then we apply these conditions onto this macro initiator. And it was possible indeed to make some PVDF backbone containing polystyrene side groups. So when you look at the initial products on the black curve, we have a shift after, of course, this was a negative shift, and the red one was a positive shift assigned to the presence of the graft copolymer. Indeed, when you compare the chlorine to a fluorine, the CBr bond is weaker than the CCl. So this is why we didn't want to use this CTFE derivative, but to find out another initiator which was susceptible to lead some radicals from the CBr bond. On the other hand, because of the presence of this bromine, it was possible to make some what is called a cross-linking. And we use this, I'm sorry, it's very small. This is a triazine containing allyl. This is called TAIC, triallyl triazine. And when you use some radicals in the system, you are going to generate some radicals. This is another evidence. And this radical react onto the different allyl group, the free allyl group, making a cross-link network. And after reaction, when you compare the TGA thermogram of this is the blue one is the starting material, okay, while the red one, which is more stable, shows that we have been able to cross-link this random coupling. So to my opinion, we are more confident because we supply all the NMR, of course, and you see here GPC, we did some IR and thermal stability. We are more confident that a CF2BR bond is more efficient in HRP than a CL bond. Though many works show that there is a lot of possibilities to cleave this CCL bond. And as I mentioned before in my previous talk, this is the molecular weight versus the styrene conversion, and we have a linear dependence of the molecular weight versus the conversion. And as you can see, the dispersity index is decreasing. This is here. We have about 2 already, and 2.5, and it decreases to less than 2. And obviously, because we have a random copolymer based on conventional radical polymerization, we cannot get a narrow dispersity here. Yes, this is the same reaction, yeah. Okay. So as you can see, we have the GPC on this side is better maybe because it shows that we have a bimodal distribution here. As I mentioned, it's conventional radical polymerization, and here after graft copolymerization, we observe the presence of a positive peak. Which has also this bimodal distribution, probably linked to this starting material. So the evidence was shown also by this first order kinetics, and also by molecular weight versus the styrene conversion, as I mentioned before. So in South Korea did a lot of HRP of hydroxy ethyl acrylate, okay, and copolymerized with this sulfonate styrene in order to make some membrane for fuel cell. And he used the same strategy from the copolymers based on VDF and CTFE in order to cleave the CCl and to have the side groups. And so they observe a VDF CTFE backbone with side groups based on this HEA and styrene sulfonate. This they show that they could get some membrane. They could first process membrane. They have a maximum proton conductivity of 62 millisiemens per centimeter. Nafion is about 100, 90, 100. So it was a correct value. It's difficult to compete with Nafion. And of course, this conductivity increases with the ionic group. This is, as I mentioned before, when you increase the ionic groups, you are going to increase the conductivity. But you can have a high swelling, which can be a limitation for the mechanical properties for after several days or weeks or months. Okay. They observe by XRD crystalline structures based on VDF and CTFE. Okay. And as soon as they had some grafting, there was a reduction of this crystalline structure with a crystalline rate. I didn't put crystalline rate. I don't remember it did. And they had reasonable fair to good thermal stability, at least up to 250 Celsius. We can understand that the ester group here is a weak point, which might break under thermal conditions from 250. You should break, and so you decompose your product. Lezu at Case Western Reserve University in Cleveland, US, did a lot of work on electroactive polymers. And tomorrow I will speak about some specific material related to energy applications. And he, in his group, made a lot of chemical modification. Though he's not a chemist, he's a physicist, and he does a lot of work on regarding the physics of materials, especially the electroactivity. So his group and co-workers worked on HRP of this terpolymer containing VDF, trifluoroethylene, and CTFE. And you remember that the copolymers of VDF and trifluoroethylene are have electroactive properties. You remember ferroelectric or piezoelectric properties. And the idea to make growing and to have some side group enables to change a little bit the discharge energy density. And I'm sorry, it's a little bit small here, but according to the composition they show, it was possible to measure that, of course, by proton NMR. Again, there was no fluorine NMR to convince me, no, sorry, there is a fluorine NMR here in which they show that there was some CTFE units which could be changed or modified into those bearing polystyrene. But I was expecting to see the signal here, the CF at -180. Unfortunately, they didn't show on the spectrum, probably because it's not present. But anyway, we could see the different units, and of course, we have to see the VDF units at -91. And the proton shows that this is the copolymer based on TRFE, CTFE, and VDF, and this is the signature of polystyrene here and here, and you can see still the presence of a intense signal assigned to VDF, and the little one assigned to the CFH. CFH is low field shifted, and this gives the nice signal assigned to trifluoroethylene. So this seems to work, and these researchers also calculate this was more the expertise of Leizu, the discharge energy density, in order to see how this system could go. And as you can see, this copolymer show very high value. The same strategy was also based by Zhang from State College, Penn State University in the US. Usually this is what is called the displacement versus the electrical signal. And usually when you put an electrical signal, you have a movement of you, as I mentioned, because showing that you have this electroactivity. And they measure usually this zone here, this area, which is proportional of the electric constant. And when you have this kind of shape, this hysteresis shows that you have a ferroelectric signal behavior, while a kind of here, like a linear, which is quite responsible, it's a dielectric compound. And in this case, you can see that the area here is much higher than this area. So the presence of some PMMA grafting by HRP from the VDF, trifluoroethylene, and CTFE shows that there is an increase and changing from ferroelectric to some dielectric compounds, which sounds very interesting and indeed very interesting. Especially the interaction of mica also enables to get good composite films and to allow some mechanical process. The same strategy with different quaternary ammonium methacrylate or pyrididium, vinyl pyrididium. This was also reported in this paper, and they could do a lot of things, a lot of characterization also for showing the crystallinity and also the melting points which are changing a lot. This is crystalline, as I mentioned, and as soon as you make some branching, you are doing to reduce the crystallinity, but it seems that the crystallinity is on the same value, though the area under the curve is decreasing, and so the crystallinity rate seems to be affected by the grafting, as mentioned before. But they offer could be able to make some films and also they studied the mechanical properties. An interesting work was developed by Steve Holcroft from Vancouver University, near Vancouver, Simon Fraser University, yes. And he decided to compare the conductivity properties of membrane prepared from graft copolymers and block copolymers. I'm sorry. And indeed here, they could prepare some diblock copolymers from copolymers of VDF-HFP and this styrene sulfonic acid diblock. And also they did some HRP from these similar products, VDF-CTFE and styrene sulfonic acid, or probably styrene and then sulfonation, in order to, and these schemes represents the different structure of the copolymers, especially the, you can see the minus signs and H plus regarding the block and the graft. And indeed, what he showed, he measured, he compared the ionic exchange capacity and the water content, because as you can imagine, this sulfonic acid pentastyrene, polystyrene traps a lot of water, and they could compare that in this case, this is much better than this block copolymers because it has higher conductivity and it traps also higher water. And this shows regarding for the same ionic exchange capacity here and here, they show that the graft copolymers is trapping more water than the block copolymer, and that the proton conductivity for the block copolymer, for the graft copolymer, was higher than that of the block copolymer. It needs a lot of ionic exchange capacity for the block copolymer in order to reach the same value as that of the fluorinated graft copolymer. So to our opinion, this is a very interesting paper. The only criticism we can bring to that is, what about the base, the chain length of this VDF-HFP and this styrene sulfonic acid here and here, and they didn't mention how long this JAX paper is very short. It's only 2 or 3 pages, and even the sulfotin information is not quite comprehensive to really figure out if the study is deep enough in order to compare what is comparable indeed regarding the chain length and regarding the values. So, but they did TEM. Hello?
Sir, as we have our last session, that is tutorial, scheduled at 5:50, let's have a break and then we can continue again further.
I take a break now?
Yes, sir. We'll gather at
okay.
5:55. That means 10 minutes from now, and then we'll continue for the last session.
Okay, that's fine. Okay, yeah. Thank you. Just this last slide is from Maciejewski. And they did also the same HRP on this VDF trifluoroethylene for lithium-ion battery applications. Okay. So, okay, I close, and then I'm going to change my slide, and in 10 minutes, I will come back with you. Okay?
Yes, sir.
Okay, thank you very much.
Thank you, sir.